Optical microscopes are bound by a hard physical barrier known as the Abbe diffraction limit. Because light propagates as a wave, a lens can only focus it to a finite spot. If two nanoscale structures sit closer together than half the wavelength of the light illuminating them, they blur into a single, indistinguishable mass. Standard super-resolution techniques, such as STED or STORM, bypass this barrier. They successfully resolve nanoscale details, but they demand highly complex beam-shaping hardware alignments or rely on specialized fluorophores engineered to blink on and off over long capture times. A 2022 paper presents a computational workaround to achieve 130 nanometer spatial resolution without modifying the excitation field or requiring sophisticated hardware. This diagram illustrates the physical parameters of the experiment. The researchers used a conventional point-scanning confocal microscope equipped with a standard continuous wave 980 nanometer laser operating at ultra-low excitation power. This line profile graph confirms the experimental result. By mapping the intensity cross-section of the emission, the data shows two distinct emitters clearly resolved at a separation distance of precisely 133 nanometers. The researchers attained this sub-diffraction clarity by shifting the burden of resolution away from the physical lenses. Instead, they relied on a computational algorithm to extract data from the physical chemistry of a dynamically nonlinear probe. This is a transmission electron microscopy image of the optical transducer used in the experiment, sodium yttrium fluoride nanocrystals, measuring 41 nanometers across. These nanocrystals are heavily co-doped with two specific lanthanide ions. The host crystal contains a concentration of 40% ytterbium, acting as a sensitizer, and 4% thulium, acting as the activator. This energy level diagram maps the absorption. Struck by a 980 nanometer laser, ytterbium ions absorb photons directly, initiating a sequential, cascading energy transfer to the thulium activator's ground state. This cascade drives a 4-photon up conversion process, reaching the 1D2 level to emit a 455 nanometer photon. Because this specific emission requires the absorption and transfer of 4 separate photons to reach that intermediate state, the resulting emission intensity does not scale linearly with the laser input. These dual-doped nanocrystals are intentionally engineered to produce this nonlinear reaction. That physical chemistry provides the exact mechanism needed to manipulate the optical point spread function. This chart plots the 455 nanometer emission's nonlinear optical response to the laser's intensity. At 0.1 milliwatts, it exhibits a steep rise with a 4.2 slope. The curve then flattens into a plateau, indicating a dynamic equilibrium among the thulium ion's intermediate energy states. We must look at the laser's spatial geometry. It is a Gaussian beam, with irradiance highest at the center axis, decaying toward the edges. When striking a nanoparticle, the absolute center hits the saturation phase first, while the lower intensity outer edges remain below threshold. This schematic demonstrates the consequence of differential saturation. As excitation intensity increases, a wider area of the beam crosses the threshold, progressively expanding the emission point spread function's effective size. Distinct saturation curves show the central point reaching saturation before peripheral points. By modulating the ultra-low input power of the laser during image acquisition, researchers can force the point spread function to dynamically expand and contract. This encodes variations of high spatial frequency information directly into the resulting images. The sub-diffraction spatial frequencies are now captured by the sensor, but they are buried within the varying blur of the point spread function. But extracting them requires a mathematical filter. Equation 1 models the fluorescence intensity profile using a Taylor series expansion. The excitation spot's geometry is represented by the Gaussian term, g of x. The series breaks this into a sum of increasing exponents, capturing both linear and nonlinear spatial components. Mathematically, these higher exponents of g of x scale inversely with the square root of the nonlinearity order. In physical terms, higher exponents equal smaller effective point spread functions, which contain the higher spatial frequency information. In any single raw confocal image, the lowest exponent of g of x dictates the width of the final emission profile, locking the overall spatial resolution firmly at the diffraction limit. To solve this, an m-step algorithm uses confocal images taken at varying excitation powers. A weighted finite difference method multiplies and subtracts these images, canceling the diffraction-limited exponents of g of x. Finally, a fast Fourier transform removes low-frequency noise, generating a stabilized, high-resolution profile. The algorithm operates as a computational scalpel, mathematically stripping away the diffraction-limited blur to reveal the high-resolution core generated by the multi-photon emission. These colorized simulation grids test the algorithm against synthetic continuous cross-line structures, populated with emitters spaced down to 130 nanometers. Comparing the outputs, second-order processing isolates the general shape, but third-order Fourier-modulated processing accurately pinpoints the intersections, resolving the structural lines into distinct positions. Moving from simulation to in vitro experiment, this image panel compares the imaging of single scattered nanoparticles on a cover glass under varying excitation powers, from 0.1 to 0.3 milliwatts. The raw confocal image yields a single, overlapping fluorescent blob measuring roughly 220 nanometers across. After running the multi-step capture through the third-order algorithm, that blob splits into two distinctly resolved nanoparticles. This cross-section intensity profile verifies the scale. The processed orange curve exhibits a sharp drop in intensity between the two peaks, confirming a clear spatial resolution of exactly 133 nanometers. The experimental data validates the Taylor series hypothesis. By systematically modulating excitation power, sub-diffraction spatial frequencies can be successfully extracted using conventional optical hardware. If subtracting image steps continuously shrinks the effective point spread function, it raises a logical question. Why not calculate to the 5th or 10th order to achieve infinite resolution? The mathematical limit is bound by a physical one, the signal-to-noise ratio. Every time an image step is subtracted, the resolution improves, but the usable signal suffers a sharp drop. Because this technique explicitly requires ultra-low excitation power to stay within the steep slope of the nonlinear curve, dropping the laser below 0.1 milliwatts causes the raw emission signal to be entirely swallowed by the sensor's own background noise. Despite this boundary, the technique secures STED-level nanoscale resolution without the staggering hardware cost, complex optical alignment, or the high-power phototoxicity of traditional systems. The future of microscopy relies heavily on computation. By engineering quantum probes with highly specific dynamic optical responses, researchers can shift the burden of resolution from physical lenses to processing algorithms, mathematically